We're going to start with discussing pretty much how to create the graph of a function using calculus. The first thing we're going to talk about are extreme values. When we say extreme, what we're talking about there is the highest and or lowest values. Okay, now when we talk about extremes also, we have different types of extremes. We have something called the maximum, that's the highest, and the minimum, that's called the lowest. That's the lowest. You can either be absolute, which that means overall, every one of them, which is also global. And it could be local, or it's also called relative. And we'll discuss relative to what in a second. Okay, as the title says, extreme values of functions on closed intervals. That's going to be an important condition. It's got to be a continuous function. It has to be on a closed finite interval, because within there, then we're guaranteed to have some sort of extreme values. Right? For example, let's y equals cosine x, y equals sine of x. On the interval, negative pi over 2 to pi over 2. That's so if we graph these two, on the same interval, so at 0, cosine is 1. At pi over 2, cosine is 0, and negative pi over 2. So there's that graph. Sine. Sine at 0 is 0. At pi over 2, it's 1. At negative pi over 2, it's negative 1. And it looks like this. So depending on what part of the interval we're looking at, we'll see that we have, in this case, we have a maximum point. And because it's the highest point overall in the domain, it's an absolute maximum. But since it's also over a smaller interval, it's also a local maximum. And there's no minimum. On this interval, because we have two values that are the same. We can say that this one's local to this side This one's local to that side, but there's no absolute one. Unlike the sine function, we have an absolute minimum and an absolute maximum. Because there's no other lower level than that, no other higher level than that. Okay, so looking at your example one sheet, your sheet with example one. Example one has 4 graphs, which we're going to examine. They're all going to be the same function, but we're going to approach it from different intervals. The function is the quadratic equation, x squared. All right, so this first one, the domain is all real numbers. It's from negative infinity to positive infinity. This one the domain is from 0 to 2. This domain is from 0 to 2. And this one is from 0 to 2. Now let's determine whether there are any extrema, any absolute extrema. So in this first one, because it keeps on going forever and ever and ever, there are no absolute max because it keeps on going up and up and up. However, the absolute minimum at x equals 0 because we have the lowest number there. Okay, now this one, we have a closed interval. This is an open interval for an infinity. This was a closed interval from 0 to 2. We now have an absolute max at x equals 2 and an absolute min at x equals 0. This one has an absolute max at x equals 2. But since that's an open non-included interval point, there's no absolute min. This one, since there's open at both ends, has no absolute min or max. So it has to be a closed interval to be for the endpoints to be included. If they're not included, it cannot be a maximum minimum. Why? Because we can keep on getting closer and closer and closer and closer and closer and closer to that point and never reach it. So that brings us because of these are extreme values, we have an extreme value theorem to talk about, which will codify this whole process, give us a code to follow. Right? Theorem 1. The extreme value theorem. What the extreme value theorem states is this. If we have a function f of x on a closed interval, then the function attains both an absolute maximum and absolute minimum in that interval. Now, how do we know if something's a maximum minimum? Definition. An absolute maximum exists at C, which is an interior point or a point somewhere inside that closed interval. At C in the interval, where f of C, remember it's a maximum, is greater than or equal to for all x's in the domain. And a closed interval set. So if this value, whatever it is larger than everything else, then it's an absolute maximum. An absolute minimum exists at point C, somewhere in the closed interval AB, where f of C is less than every other point for all x in the domain. All right, so that's what we'll be looking at in this section. So in this theorem, the conditions. The interval is closed. the interval is finite, maybe there's a beginning and an end, and the function is continuous. If all three of these conditions are met, then the theorem applies. And then we could find, no matter what the function is, as long as it's within a closed interval, and that means the endpoints, then we will have a maximum point and we will have a minimum point. Let's look at some examples of, okay, what about functions that are, remember, if they're functions, they have to exist on the library of functions. One of them we have the exponential function. Remember, the graph of this one looks like this. Always crosses through 1. It's from negative infinity to positive infinity. So does that one have an extreme value? Doesn't have a, there's no absolute maximum because it keeps on going higher and higher and higher. And there's no absolute minimum because the graph keeps on getting lower, 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 and lower, and lower. It never gets to 0, but it gets infinitely close to 0. So those are the absolute values. The local or relative extreme values. These occur in closed subsets or sets. Because even if we're going from like the exponential function, even going from negative to positive infinity, there could be points where we do have extrema points. So, for example, if we had a function, let's say a fifth order polynomial, and it has the rest of it there. The graph of a fifth order polynomial, remember, this is the degree, which tells us how many solutions we can have. So it looks something like this. Where we have A, B, C, D. We have points at these places. So local extreme values, in algebra, they're called vertices. So the reason they're called local is because this one's the highest. This is called the relative max, because on some smaller interval, it's the highest number. This one's called a relative minimum because it's the lowest. This is also called a relative max. This is also called a relative min. It has no absolutes. No absolute max because it keeps on going. It's an arrow. And no absolute min because it keeps on going forever that way. But if it did have a point here, if it did have a endpoint there and an endpoint there, where now my intervals at x1 to x2 now since this one's lower than everybody else, now it's the absolute min. And since this one's the highest of everybody else, now it's the absolute max because we now have a closed interval. Actually, for local extrema, because whenever you have closed intervals, that means you have to look at the endpoints as well. But if you have an open interval, that means you don't have to worry about the endpoints because they won't exist. That way we can just look at that. So in local extrema, it's only occur on this open interval. Right, so that's what we're looking for that. That's going to be our quest for this section. Finding extrema, the plural of extreme. Remember, extrema is the highest or lowest point on an interval. That's local for local. And on some open for our global or absolute. Now, remember, these are vertices. Vertices exist where the slope is 0. And remember, the first derivative is our slope of the tangent line to the curve at that point. So extrema occur where 1, the first derivative is 0. And 2, the endpoints. And theorem 2 simply says theorem 2 defines the first derivative test because that's what we're looking at here. The first derivative theorem for local extreme values. Why not endpoints? Because remember, to be a local, you have to be open, it has to be within an open interval. And an endpoint is always on a closed interval. So that's why we can't use the endpoints to find local minimum. So let's say, okay, it tells us this. If the function f of x has a local extrema at an interior point, C of its domain. In other words, C is contained in A, B. And if f of x, f prime of x is defined at C, then f prime of C equals 0 is the local extrema. So we have to find we look at interior points C, where f prime at C equals 0. Interior points C, where f prime is undefined. And then we look at the endpoints. Of the function. So this is what we need to do to find extrema. Definition. An interior point of a domain of a function f of x, or f prime of x equals 0, or f prime of x is undefined, is a critical point of the function f of x. So whenever asked to find critical points, pretty much find where the function's undefined and find the vertices. All right, and now let's look at the steps, and then we'll look at an example. Well, let's jump into the example. Find the absolute, max, min values of f of x equals x squared on the closed interval 2, 1. So we need to find two things. All interior points where f prime of x equals 0, or f prime of x is undefined. There's critical points or critical values. The values of f of a and f of b, the endpoints of the interval. Take the largest and smallest as your absolute max, min. All right, so that's what we have to do. So step 1. On the interval -2, 1, f of x equals x squared, f prime equals 2x, set 2x equal to 0, So x equals 0 is a critical value, a critical point. You evaluate the function at -2, 0, and 1. F of -2, f of 0, f of 1. So we have -2 squared, 0 squared, 1 squared. -2 squared is 4, 1 squared, 0 squared is 0. Oh, this is the absolute max. And this is the absolute min. And that's how we do it. Let's look at example 3. Find the absolute max min of the function f of x equals 10x 2 minus ln x on the interval 1 b squared. So the first thing to do find the critical points. For f prime of x equals 0. So our function is 10x 2 minus ln x. We have to find the first derivative. This is f and this is g. So f g f prime g prime. 10x 2 minus ln x. This is 10. This is -1 over x. Goes to 2 goes to 0. We've got 10 times 2 minus ln x plus 10x times -1 over x. X's here cancel. So it's 10, 2 minus ln x. That changes that to a minus 10. Oh, hold on. Oh, hold on. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 times 2 minus ln x plus 10x times -1 over x. 10 Yeah. Let me just distribute. So I have 20 minus 10 ln x minus 10. 20 minus 10 is 10. So that's my function. Remember, my interval is at 1. Okay, first thing I do, I gotta set this equal to 0. Subtract 10. Change the sign. Divide by 10. So 1 equals ln x. All right, so let's see what x is. So, and ln x is the same thing as log base e of x. Set that equal to 1. So x is equal to e. That's my critical point. And here's my a and b. So I have to look at f of 1, f of e, and f of e squared. You have to look at the two endpoints and any critical points you have. So it's 10 times 1 times 2 minus ln 1. 10 times e, 2 minus ln e, 10 e squared, 2 minus ln e squared. Okay, ln of 1 is 0. So 10 times 1 is 10 times 2 minus 0 is 20. E, so we have 10e, ln e becomes 1. So this becomes 1. So 2 minus 1 is 1. So it's 10e. E squared. So we have 10e squared, 2 minus 2 ln e. Ln e is 1, 2 minus 2 is 0, so the answer is 0. So e is a constant 2.7. So this is 27.8 or 27.1, something like that, 27.1, I think. So here's your maximum, and there's your minimum. All right. So just take those equations and find the first derivative and analyze them. Let's look at another example. Example 4. Absolute max min function f of x equals x to the power 2/3 on the interval -2, 3. So the first thing we have to do is find f prime. So f prime equals 2/3 x to the power -1/3, which is 2, 3 cube root of x. Okay, so set your first derivative equal to 0. So we have 2 over cube root of x is equal to 0. No zero values. Because the only way a fraction can equal 0 is if the top is equal to 0. But x cannot equal 0. It makes f undefined. F prime undefined. So x equals 0 is our critical point. Step 2, we have x equals 0, and we have -2 and 3. So we have to look at all three of these. -2. So -2 squared is 4. So the cube root of 4. 0 to the 2/3 is 0. Three to the power 2/3 is 9 to the power 1/3. Cube root of 9. The absolute min is at 0. And the cube root of 9 is bigger, so this is the absolute max. All right, that's it for that section. Let's do the next one. That one didn't take long. Let's go ahead and do the next one.